Welcome back, Quadrature fans. It's been a while. So, today we're going to continue our geometry for quadrature, but wait a minute, I need to introduce myself. My name is Professor Theoremus Antiquitus, also known as Marian Elena. Ooh, his head in here. Okay, today we're going to continue with geometry for quadrature, and we're going to look at Cavalieri principle. What is Cavalieri principle? Well, you've seen a deck of cards. This deck has an area. And if I shift it like this, I have not changed area. That is known as Cavalieri principle. Okay, very simple. Even a child can understand this. You understand sliced bread, sliced cheese, and a deck of cards, you understand Cavalieri's principle. And yet, there are some profound features about Cavalieri principle that we'll touch base. So, here we go. Let's continue. We always use simple diagrams. And our diagrams, basically, we have a box. And we're dealing with area and with slope. It's pretty simple. You've seen that before. You know, this box is what I call a characteristic diagonal here. And let's say I draw another line over here. And, so we look at, let's look at this. We're going to look at the ratio of slopes and the ratio of areas. And we're going to call MT the slope of this particular line, and M diag is this particular line right here. And what is that? We say that's C. That's the ratio of slopes. And that's MT over M diag. So what is that? Well, it's BF, which is your rise, over BD, which is your run. Okay, that's the slope of this line. And then the diagonal, the slope of the diagonal is simply B over A, rise over run. Simple. I mean, you can follow through, right? Pretty simple. You guys get it? Yeah, okay, that's good. I don't feel this way. Yes. Kids can get this. Now, similarly, K is a ratio of area, the ratio of this area in this triangle to the area of the box. So we're dealing with these ratios because those tend to be invariant. So let's look at that. What is the area of the triangle? This triangle here, well, it's 1/2 of BF times BD. See that? That's this thing. Pretty simple. And what's the area of this big box? That's B times A. Okay, pretty simple. You guys can follow through. No problem. Now, we are going to do a Cavalieri shift. What's that? Well, guess what? That's, you take a deck of cards like this. Let's say this was drawn on my deck of cards. And I just do that. Okay? I have shifted this deck. So I've done some kind of a change. The change is I've shifted. And the question is, what remains constant? And we know that area remains constant. That's known as Cavalieri principle. Okay? Area remains constant under a Cavalieri shift. Okay. Well, let's look at that. Well, we're going to look at this kind of from a Euclidean perspective and then from an affine perspective. And here's something interesting. Well, we start here and then we just do a shift. And we're going to be looking at, again, slopes or ratio of slopes and areas, or ratio of areas, just like we did here. And from a Euclidean perspective, we would ask, well, you know, what is this ratio of this diagonal, this slope, to this diagonal? We started out here, and I shifted it. And I shifted such that it's exactly flat. You see what I did? I have a right angle here. That means that this is perfectly flat. That means this is zero slope. You follow with me? Zero slope. So what is the ratio of slopes? Well, it's 0 over something. We don't care what it is, but 0 over something is 0 from a Euclidean perspective. Okay, not bad. But now we're going to look at what about the ratio of areas. We gotta make one modification though. When we did the shift, things are not the same anymore from a Euclidean perspective. We really need to relabel things. We need to call this B prime, F prime, A prime, E prime, D prime. Do you see why? Because it's not the same thing as this, right? From Euclid's perspective, which is kind of what we're used to. We like to see things right angles. So, okay, because we did do a shift, well, let's put the prime. That just simply means it's a little bit different from what it was before. Follow with me? All right. So, what is the ratio of area of the triangle, this triangle here, to this shifted box? Well, that's 1/2 of B prime F prime times F prime D prime. See it? Follow with me? It's 1/2 of this times this. And what about the area of this shifted box? Well, that's B prime times W, which is this distance between these lines, okay? That's what W is, and W happens to be equal to the A over here before we shifted. Follow with me? Should be pretty standard. W is A, you know, but that's what the area ratio is. It's 1/2 B prime F prime times F prime D prime. It's this times 1/2. And the whole thing is over B prime times W. Okay. Let's look at this from an affine perspective. From an affine perspective, and this is where I need your help. My understanding, at least, of this affine is affine is not even capable of detecting a change. When I do this, he can't make any, he can't differentiate, he can't even say that it's different. Because he has no metric notion of distance and no metric notion of angle. He doesn't know anything about right angles or perpendicularity. It's just, it's kind of a simpler geometry. Whew, this thing fell. So we're going to look at this, and from an affine perspective, nothing changed. And so the area of this triangle, well, he's going to call it, okay, Euclid wants to change me, he wants to call us B prime, F prime, so okay, fine, I don't care, I don't know anything about metric notion of distance. So we'll just say that the area of this triangle is B prime, F prime. Excuse me, we're doing the slope. The slope of this which is this slope here. Remember, we were started here, and now he doesn't see any change. And so, okay, it's rise over run. That's how he sees it from F-line. Okay, so it's B prime F prime divided by B prime D prime. This is the rise, B prime F prime. This is the run, B prime D prime. Just like over here, he doesn't see any difference. Okay, and what about the slope, the diagonal slope over here? Well, he says that's B prime over A prime. That's what he sees. He doesn't, okay, fine. B prime over A prime. So, one thing we can simplify, this distance B prime F prime is exactly the same as BF over here. Euclid has no problem in certifying that this distance is the same as this, because that hasn't changed. What has changed is this distance from here to here has been stretched, dilated. See, this is what I started out with, and now I gotta go more. I gotta stretch it. Look, I have a ruler, okay, and look, I gotta go further. It's dilated, it's stretched, this distance. So, whew, what have we got? So what we're going to say that B prime F prime, well, that's the same as BF. There's no conflict there, okay? And B prime, that's the same as B. See this B prime, that's the same as B. They're the same. No conflict. Euclid certified. Okay, good. So we end up with an interesting scenario that C from an affine perspective, that's just the ratio of slopes, is BF over B prime D prime, the whole thing over B over A prime. Follow with me? It's just algebra. We're doing algebraic manipulations. Okay, cool. Let's do now the K, which is the ratio of our area, particularly the area of the triangle to the area of this shifted box. What is that? To affine, it's 1/2 B prime F prime times B prime D prime. Okay? That's the way affine sees it. And the area of this shifted box, well, it's B prime times A prime. That's how he sees it, because he sees no change. He can't detect any metric change. So, whatever Euclid says, okay, I'm gonna call you A prime, and he takes it and he says, fine, all right. And we can simplify, because Euclid says, okay, well, B prime is the same as B. So we can say that K, our area factor, is 1/2 BF times B prime D prime. The whole thing over B times A prime. Because
you just fine.
Okay, now here's where things get interesting. From Cavalieri's principle, which was known in 1642, because Cavalieri published his results in 1642 AD, we know that under a shift condition, the area doesn't change. And therefore, the area of this triangle doesn't change. It's the same as this one. The area of this box is the same as this one. Therefore, K remains constant. It's invariant, okay? And that means that this entity here must equal this entity here. So let's look at that. What have we got? Well, 1/2 BF times BD, the whole thing over BA, is equal to 1/2 BF times B prime D prime all over BA. Well, we can cancel this out. And basically what we get is that BD over A is equal to B prime D prime over A prime. That is established. This is a relationship. And the flip is also, you can say A over BD. BD equals A prime over B prime D prime, right? Pretty simple. Well, look at this. Now that we know that this relationship holds, take a look at what happens here. If I put the A prime up here, look, it's going to look the same as BF over BD equals B over A. Because this ratio, see this ratio here? B prime D prime over A prime is the same as BD over A. We just established that right here. Now look at this. This is the same as this. So our slope ratio C is invariant. And that's something. It's telling us that from an affine perspective, slope doesn't change. It's invariant. It stays constant under a shift condition. So, here we did a shift, or a shift like this, and not only is area the same, invariant, but so is the slope. And the slope ratio is the same. But from a Euclidean perspective, that's not the case. He says C is 0, and here's C is, okay. And this is the rub that, how can that be? This is what blows a circuit breaker in my mind, and hopefully in your mind if you're thinking. So, let me know what you think. This is stuff that needs to be digested. So, remember, I'm Professor Theoremus Antiquitus, also known as Mary Elena, and there's much to learn.